So hello, everyone. Good evening. Today, David Soldani is going to talk about 6G fundamentals, vision, and enabling technology from 5G to 6G. So it's my pleasure to introduce David to you. He has been active in the information and communication technology field for more than 25 years, holding senior management and executive positions across global organizations for more than 20 years, contributing both as a key industry player in Nokia, Huawei, and also as a distinguished academic in University of New South Wales and also the University of Sydney, I think. He has been serving as associate editor-in-chief of different magazines and journals, and also he's been taking part in many IEEE international conferences and journals as a TCP member. And his area is a future wireless network and artificial intelligence, cybersecurity, and IoT. And here, I think he recently joined Rakton Symphony as a Chief Information Security Officer. So we are so happy to have you here, David, and please start.
Yeah, so thank you so much for the invite, and apologies for the delay. And so you have already introduced me, and I thank you so much for that. We can jump directly to the presentation. What I'm showing today, it is a summary of a paper recently published in the Journal of Telecommunications and the Digital Economy here in Australia. And this work is a review of a number of documents and some personal views on how 6G may look like. So the paper goes beyond that. So it also reviews, as I'm doing now, the evolution of 5G. And I'd like to start exactly from there. And particularly, I'd like to present you where we are with 5G today, although those slides capturing the latest development we had last year in December. So we may expect something that the numbers here reported on this slide are slightly higher, but doesn't matter. So what we had in the last year in terms of assigned spectrum is what presented on this slide. So we have more than 100, I would say now more than 130 operators being assigned spectrum, and the spectrum assigned is across the three bands below 1 gigahertz. The mid band is between 1 to 6 gigahertz, and then the high band normally refers to millimeter wave above 6 gigahertz. Actually, it will be above 20 gigahertz. So the main band in use is the mid band, of course, the C band. So most of the deployment are around the 3.5 gigahertz. And as we speak, we have many operators that have launched or plan to launch 5G services. In Australia is among them. And you may see on these slides more than 110 operators. They're already providing 5G service. Also in Australia, I have measured downtown more than 350 megabit per second on a smartphone. Now, looking beyond that, what are we expecting from 5G and its evolution? This slide is more significant because it displays number in terms of, yes, perhaps, yeah, we can mute on the background. Thank you so much. And tell me if my voice is not clear enough. So those numbers represented here, reports here are in terms of connections. So you may read it as connected smartphones end users. So we are starting from end of last year and later this year from more than 300 million connections, and we are expecting to reach around 1 billion connection by 2025. So in less than 5 years from now, that means we have about 20% of the global penetration. And China, of course, is where most of the connections will be practically implemented. Then looking at the details of the global deployment, also from today by 2025, again, on China, we can see that already today we have about 86+% of the global implementation happening in China. And the investments on the 5G infrastructure by 2025 are expected to go beyond the 200 billion. So you see that the 5G is definitely a critical infrastructure and a fundamental infrastructure that will enable the digital transformation of the country, along with the support of many other services. So of course, intended, it's not all happening in China. Actually, if you look at the relative numbers, we have that most of the deployment of the 5G will be by 2025 in North America, Europe, and Asia Pacific. And these three regions will account for more than 90% of the 5G mobile connection forecasts globally by 2025. Now, looking at the terminals, availability smartphone, because practically if the ecosystem is not in place, also the services and the uptake of the business cannot take place. And that numbers here are more recent, is of a month ago. So you see that we have already more than 700 announced devices, and more than half of them are commercially available. And we are talking about not only smartphones, of course, it's about 50% of the device available commercially, but there are also a number of CPE for fixed wireless access and other models. Models in terms of tablets, industrial routers, laptops, and other type of devices. Supported bands are also illustrated on these slides, and you can see that what is practically available is especially in the C band. So as I said already, around 3.5 gigahertz using TDD as an access technology. Now, looking beyond that and examining the 5G standard roadmap, so what practically will be developed by the 3GPP technical specification groups, and then those specifications will be transposed into standards globally. We have that, you can see here, that the 5G in its both no standalone and standalone configuration was already completely specified by September, in September 2019. So the release 15, the first version, first release of 5G was completely made available already in 2019. So what we have now is already completed the specification on the second release of the phase 2 of 5G, and release 16 is basically already frozen, and the work items have already started and expected to be completed later this year, beginning of next year. That is about release 17. So release 15 and 16 together, they pretty much meet all the requirements we expect, or actually we put on the ITU standards. I'm thinking of the visions agreed back in 2015. As we speak, we are already in the standard discussing the content of the 5G advanced and the new set of use case, so the new use case categories. That is about release 18 and releases. In parallel to that, we have already ongoing massive investment on 6G. The research is ongoing, and I think it will continue for about, 2, maximum 3 years. Then we will start discussing the work items and, the study items, which is about selecting the fundamental enabling technology to 6G, and then the technical specification work will start in terms of work items, and the new system is expected to be commercially available by 2030, or say around 10 years from now. All right, so we can continue. Looking at the detailed content of the technology roadmap, allow me to spend a couple of minutes on that, because it's, I think it is interesting to see, first of all, what is the 5G, or especially what is the new radio? What does the new radio support with respect to 4G? What is fundamentally new here in terms of the technology? Yeah, I think there are many new things and capabilities. So the first thing I think fundamentally important is that we designed the 4G system, so the LTE, to work up to say 2 gigahertz, anyway, in the sub 3 gigahertz, whereas the new radio interface is capable of supporting on the first releases, so release 15 and 16, up to 52.6 gigahertz. And now in release 17, we target to reach out 71 gigahertz. Anyway, we would like the new radio to use all spectra from, say, 400 megahertz up to below, say, 100 gigahertz. Above that, it will be a topic of 6G. So what does the new radio do in practice? So it supports from the very beginning very interesting features, or say technologies. We have massive MIMO from day one, which was optional feature for the LTE. For the new radio, it is a mandatory requirement. So when you go on air and you offer that commercially, you must support massive MIMO. So you need to have a capability in place to be informed, to use multiple antennas and direct the signal through multiple beams simultaneously. So you may serve all those beams to a single user, or you may think of having a multi-user type of approach, where you have the different layers provided to different users at the same time. You have a sort of space diverged in that sense. Okay, the soft interface, so the numerology was introduced with the possibility, therefore, to have different subcarrier spaces and cycling prefixes, so that this particular spectrum was supported. The split of the radio access was already specified in release 16, as it was specified completely end-to-end in terms of network slice instances, the slicing concept already in release 15. And now we are thinking of specifying the RAN slicings, which is a topic of release 17. Now, the focus initially was on enhancing the mobile broadband experience. And now with the coming next release, or release 17, we think of providing industrial IoT services. Practically means to reduce the positioning down to 3 meters using triangularization methodologies, no longer, say, relying upon the GPS. And then other important characteristic of the system is the integrated access and backhaul. I will explain that in a minute. And bring the new radio on the side link, so that we can also have a better vehicle-to-X communication. The future radio, the future railway mobile communication system It has been defined now as the 5G release 16 and 15. So that means that the GSM-R retiring by 2030 will be completely replaced by the new radio release 16 and 17. Then with release 17, what's coming next? Yeah, there will be many new features to meet the requirements of critical IoT. Critical IoT means IoT application on critical infrastructures. A critical infrastructure could be like a gas, could be electricity, it could be ports. Now I'm following just the Australian government, the definition of a critical infrastructure. So port, but also data center and other vital, say, infrastructure for us, for humans to use. So what kind of enhancements? Well, respecting the positioning is going down to 30 centimeters, which is very important, because if you think of connecting a robotic platform and you're having, you want to have a remote control of the platform, it's of course intended that any action and reactions has to be with a level of accuracy and consequent precisions below 30 centimeters. I would say even smaller than that, because if you think of losing control of a robotic platform or vehicle, you need to stop that immediately. So the control must be really centimetric, I would say. Then beyond that, what is coming, fundamentally important, is the support of non-terrestrial networks in terms of geostationary Earth orbiting satellites, and more importantly, the low Earth orbiting satellites. What we're talking about here, they are satellites of an altitude that ranges between 300 to 1,500 kilometers. And practically they allow us to reach massive coverage, because the footprint size ranges typically from 100 to 1,000 kilometers. For example, this is what we are currently proposing in one of the projects I'm working in Australia, denoted as Connectivity Innovation Network, the CHIN, which is an initiative of the US government to achieve ubiquitous coverage and therefore ubiquitous public safety services across those states here in New South Wales. And one of the solutions we are proposing is exactly to make use of LEO satellites. Beyond that, we have the support of MBMS, so the signal of multicast, or for multicast and broadcasting audio and video. And I think even more importantly is that finally the MultiAccess Computing platform will be integrated with the 5G core network and the upper layer service. It's of course intended that the security coming as a complete baseline in release 15 is also enhanced, meeting the requirements of the new supported functionality. Okay, now a couple of words about the system architecture, so we also understand what we are expecting later by 6G, or anyway, the evolution of the 5G system. I would like to introduce you the concept of the CU and DU split, so the so-called RAN disaggregations, and a fundamental enabling technology that is a network slicing. So the CU-DU split was already specified completely in release 15, and on this slide you may see what is all about. So you may think about this is the radio access network. There is no core network here, but you can identify both the radio access system and the multi-access edge computing platform that interfaces to the radio access network using the 5G core network, or even a function of the 5G core network denoted as user plane function. So the radio access network that goes from, say, this point down to where you place the antenna. Antennas now is disaggregated at least into three main parts, as illustrated in this slide. So we talk about the central unit. We do also have the corresponding distributed unit. And then we have, say, the physical layer, the radiating elements that could be, depending on whether you have active or passive antennas. We talk about active antennas of radio remote units. It doesn't matter. So what happened in practice that we decided to split the protocol stack. So the protocol stack means the radio interface protocol stacks, which haven't changed for 20, 30 years. That's still the same. We patch them, they don't change. Now we move them back and forth, and perhaps now, thanks to the virtualization, we will have flexibility to decide ourselves where to place them, and if you have the appropriate implementation. But anyway, so the split is, say, mainly in three parts. The first split, so the upper layer, or the upper layer split, it is denoted as option 2. So we divide the stack here. So this low part of the stack with respect to the remaining part of the stack, namely where the scheduling runs and the fast radio interface functionality are placed very close to the radio interface. And then we do have another interface, which is between the distributed unit and the, say, the antenna part of the system. So why has been done that? What are the advantages? So the advantage now I'm discussing independent how you implement those functionalities. For example, what Rakuten does is virtualize everything. So you have plenty of flexibility to move all parts end to end. But independent of the implementation, we have here the ability and the capability of moving or placing or installing the central unit at different distances with respect to the radio interface, or with respect to, say, the far edge zone where your antennas are located. That allows us to share the resources among the different access points, and therefore control centrally and processing the connections over very, very, very large areas. And this is particularly beneficial if the traffic at the ingress of the system is low. So that means this deployment is especially suitable for rural areas and the Internet of Things. There are some drawbacks, because if you think of moving far from the edge, those functionality, what you do practically, you increase the latency. Now, what's also coming next with release 16 is the integrated access and backhauling. What is it in practice? In practice is an enhancement of the base station or GNOB, whatever you want to call it, into two main functionality. One that plays the role of a donor node, the other one, it is basically a slave node. But what we are doing here is to allow the communication between those access points using exactly the same spectrum and the technology as we are using to access the system itself. So you see here that the new radio UU interface is between these 2 points as it is between the terminal and the base stations here. So that allows us to simplify the system, extend reach, coverage, and reduce costs. Now, an important characteristic or a fundamental enabling technologies that will make this approach even more viable is the utilization of network slices. So if you think of having virtualized all this infrastructure with the capability of supporting, instantiating the different functions, say, independent of your hardware deployed, then using network slicing, you can really benefit of the possibility of disaggregating your radio access virtual function. Like we may say here that in the case of having in place applications that demand for high reliability or say low latency, you may think of moving and instantiating those particular function around those particular functionality, namely the CU, very close to the far edge. Conversely, if you have low traffic or in rural areas, you may save your costs by aggregating the different type of connection and placing, instantiating, running, starting your containers, say, in the local data center. And that has a great advantages, introduces the flexibility for you to have a single physical infrastructure that supports dynamically any type of applications, and they're especially viable if you think at the vertical sectors. Now, what ORAN, that initiative, or in particular, I'm thinking of now OpenRAN Alliance doing, what I have done is they've gone beyond that. So if you compare the architecture that was standardized in 2GPP, they've gone beyond that. So they have introduced additional interfaces as illustrated in this slide. So like before, I've shown you the F1, E1. So that's the CU-DU split. They have introduced many more interfaces and also other type of functionalities that are extremely important, such as the RAN intelligent controller near real time, which means very close to the central unit, close to the radio access network, and the RAN intelligent controller, no real time, which has a broader say visibility and ability to handle more communication across the network. What I have a chance to show you now is the implementation of Ultrastar. Ultrastar is an organization, one of the vendors of disaggregated systems among many others, and that was recently acquired by Rakuten. So I have this great opportunity now to show you that the system already exists in practice, and that is what will be deployed by a number of operators starting from Europe, US, and other countries. So you see, you have a one-to-one correspondence between the ORAN architecture coming from the OpenRAN Alliance and what the offering of Ultrastar is. Now here we could spend a day on ORAN, vRAN, OpenRAN, what it's all about. For me now, the key point is to want you to think of the having in place a capability and ability of disaggregating the system, use possible a single platform, and on top of which be able to instantiate any kind of functionality and evolve those functionality by simply say download the new images or new version of images on your container. So extremely simple system to have in place, and it stays say aligned with the development of the new features. So here you have the Ultrastar implementations. It is one of the implementations, of course, made available. And Ultrastar is really advanced in the sense that is shifting towards the containerizations. And I think you also have a chance to follow the new technical specification coming from the NFV, so the ETSI framework in that respect. So what Ultrastar has made available now, commercially, it is all-in-one platform system which supports automation, virtualization, and orchestration using these two specific technologies, OpenStack, when we think of virtual machine, and containerization, container technology, orchestration using Kubernetes. So my suggestion, if you are studying, or if you think of contributing or work on a 5G system, information and communication systems, 6G, etc. My suggestion is that on the one hand, you need to have a clear understanding of the 3GPP stack, which is pretty much what I'm covering you today, but practically the difference will be in the specific implementations. and that's going to happen through the containers. So you will see that that's the way that can save costs. That's the way that you can create more services. That's the way you can easily support a number of business models. So my suggestion is that you start studying. I will not spend too much time on OpenStack, but I would focus on the technologies for containerization. Docker is one, Robin, etc. But more importantly, start understanding exactly the container orchestration, because that is basically the nervous system. That's the way all those functionality will be simply supported, implemented, and put into communication. So this, I would like to rapidly move forward and introduce you the multi-access computing platform. Maybe just a couple of words on that, because this is a key functionality, it's a key platform, finally, as I said, coming and integrated with the 5G system. It is a release 17 feature, but it's the technical reports are already available. It's been beautifully integrated with the 5G core and the services. It's changed between this platform, which is nothing else than, in high level, an application function of the 5G system and any kind of device. It is a fantastic platform, and it is convergent. It's not an application function specific to the new radio or 4G. It is, as I said, interface to the UPF, the 5G core, and the 5GC is the first core network truly, really convergent. So it doesn't matter how you are accessing the connectivity resources, the Mac will still work because the 5G core network is access agnostic. So we could have a one-day discussion on that, perhaps next talk. Why so important? Why is so important the virtualization, and what is so important to have a multi-access computing platform at the edge of your network, fixed, wireless, and convergent, it doesn't matter. So it is extremely important because that's the way you may reduce latency. And more importantly, as here, I'm here, so that's the access. As 5G, now I need to talk about 5G. Or anyway, you would need a very, 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 very fast radio interface, ultra reliable, low latency. If that is in place as 5G, the new radio, and 5G advanced and 6G, well, what you could do here, and that is necessary, that you can move all the costs and complexity in terms of hardware, software, and applications from your device. You can run them on the edge platform and expose that as a marketplace. So me as an end user, or me as a guy who likes play games, I don't need to constantly like my son spends nights to download the new versions of games. That's useless. You don't need to do that. So that's gonna be there in the network on the edge platform at the edge. And when you have a cheap device, all the rendering interactions will be handled on the server. What you need to exchange here, just a little signaling, and the downlink will be just a sort of a streaming services for you to consume using very, very, very cheap device. So that's the future. And the future will evolve in these terms, and this device here will be also intelligence, and also the intelligence will shift from here to here. And I'll prove that in a second. Now, moving forward, security, a couple of words about security. Security has not changed. So what the system 4G was really secure, robust, and the vulnerability we identified through the years were fixed with 5G release 15, for example. I'm thinking about the integrity protection of the radio interface. How does the security work on 5G? It is extremely simple. It looks complicated. It is complex, but extremely simple. It is all based on a share secret. And the share secret, it is a key. And this key will change in size at a later time. It doesn't matter, but this key is secret. It is shared and is available in the SIM card, in the device. The SIM card, it is there and is made available within the core network. Specifically, it is in the repository, in the authentication repository function. That is, and then out of this key, which is not transmitted, so out of this key are produced all the remaining keys in all parts of the network, and using those keys we achieve confidentiality and integrity of pretty much all information across the system end to end, and is also supported as symmetric authentication. That means not only the network authenticates the end user or the subscriber, but also the subscriber has ability and capability to authenticate the net. Well, that's great, fantastic. Yeah, nothing has changed. It's pretty much what we had in the past. Works. What we have here is basically announcements of these functionalities that are able for both 3GPP authorized access as well as for non-3GPP authorized access. So what I presented here at the straight eye level, it is called 5G authentication and key agreement. And if you may think of access to the system through your Wi-Fi, then it is a 3GPP unauthorized access. In this case, we need to support the extensive authentication protocol, which works pretty much similarly. We just have a different identity at the terminal. Now, beyond that, thinking of applications run on top of 5G, and the IoT traffic has been introduced an important functionality, also derived based on the shared secret, denoted as AKMA. This is a fundamental functionality. This is authentication and key management for applications over 5G, and that will allow us to authenticate any kind of applications running on your mobile, on your IoT, and using exactly the same security infrastructure. Yeah, that's great. And if we think of the other functionalities and functions in the network, and for example, the interfaces between the CU and DU, they are also specified, as I said earlier, and it is also recommended by the standard to support the cryptography. So that means to encrypt the communication between the points, as it is well specified and mandatory. The support of the protocols for the encryption and authentication and authorization, as well as the encryption of the communication between network functions. So that my first conclusion here is that uses the protocols coming from the internet. So there is, again, you see, there is no new technologies. There is no new technologies here. It's just a matter of using those technologies. Technology have been there now for many years. Yeah. So in short, authentication is always based on certificate. Yeah, in this case, certificates, you need certificate, and we use the public key infrastructure, easy. The encryption comes along with the TSL, which is an handshake also protocol that can be used for reciprocal authentications, and then the key is exchanged once the encryption is enabled. So you have a share key, symmetric. And then the integrity, you usually have an hash function with a message digest, same approach as we are having for the 5G. And then last, the authorization uses the Auth 2.0 framework, token based. So once you have implemented those functionalities, those are not necessary. So I would not spend too much time at these interfaces, although yes, you may do that to protect your implementation in terms of, for example, containerization of virtual machines. But if you're worried about the communication between the terminal and your CU that is already encrypted, as I presented earlier, so there's no way for you to penetrate at this interface. Looking here, I think it's extremely important that you protect the communication between each network function, because that will make also possible and robust that there is no possibility to penetrate between, to compromise these two communications, even if you are capable of entering into your virtual, into your, say, virtual infrastructure, in your virtual approach, how you implement them. All right, so I'm saying this because then when we move to 5G, 6G, we need to think of how to go beyond this. I mean, we are already having in place with the GSMA a framework, a scheme for assessing both the network security of the product and development and the product lifecycle processes. So the GSMA has already schemes. So that's about security assurance. And then there are already schemes available for the security evaluations of the network equipment. And what we're expecting now, that this approach by GSMA and the 3GPP will be then incorporated into certification scheme for the security authorization in different countries. Right, so this, I'd like to now enter into the new thinking. So look at the 6G. Why are we discussing 6G if everything is basically apparently supported by the new radio, so by the 5G and its evolution? The question is that to put it simple, what we see here is that the GSM was for voice, and then we made a mistake to develop a mistake. I think it was but anyway, we had an attempt to have also data communications using 3G, and then the 4G solved this problem. So 4G, you may think of a solution to data communication. 5G meets many other type of requirements, especially addressing the has capability and ability to connect beyond the devices. And there we think of machine type of traffic. And 6G, it's now meant to allow us of shifting from connecting people and things to connected intelligence. So that's basically the shift in paradigm we are expecting. So what are the main trends, and what is my vision by 2030? So my vision is very, very simple. I try to compress that into one sentence. I believe that all intelligence, all this intelligence, whatever the platform is, doesn't matter, will be connected with a zero trust model, and that's going to happen through digital twinning using 5G evolution, 5G evolution, therefore also 6G and the machine reasoning. The machine reasoning will must work together, the machine learning, and they will be located especially at the edge of the network. So how did I come back to this? So based on this, you can already think of an architecture. So what are the enabling technologies that are necessary to realize this vision? And why I came up with this thinking? Because of five reasons, sorry. First is about the fact that artificial intelligence shall be only used when it is extremely necessary, because it is inefficient, also not being really effective as humans are. The proof of this is from Roberto Cingolani and Giorgio Metta. They're from the Italian Institute of Technology, and let us see how that is demonstrated. So here you have the comparison of two boys. I say one is ICAB, that is a robotic platform, one is the most advanced humanoids in the world, and the other one is the son of one of the sons of Roberto Cingolani. And here you have the comparisons in terms of how they are made, but particular is the power they require to perform, to function. and the number of operations able to do that per second, and the energy they require to achieve certain goals. So what you may see from here, that if you give a chocolate to the son of Roberto, you could keep performing tasks that not a single existing robotic platform for more than a week. And then if you compare to that, a robotic platform basically would run already out of power in less than 2 hours. So what they came out is that in practice, we have that a machine is from 1,000 to 5,000 more costly for the same amount of operation that humans can do. So power cost per operations, it is 1,000 to 5,000 higher in machine than with humans. Then the second trend is about, so that means, this means that the intelligence has to be reused. So that's the first trend, intelligence to be centralized and reused, which means that has to be taken out from the platform and put in a place which is shared among many other platforms. The second trend is that latency, because if you think of now making decision centrally, it means that based on what the element detects, you need to respond. In order to close the loop, you will need to stay below a certain latency. And to reduce the latency, the only possibility is to move those functionality at the edge meaning close to the end user. The second, machine learning needs definitely machine reasoning, because machine learning itself, it is just a pattern recognition, a technology. It has many limitations and biases. I gave a talk, a lecture, a couple, 2-3 weeks back, when I've shown the many flows of machine learning. In order to solve those flows, we need to enhance those functionality with other technologies in the direction of machine reasoning. The other important trend we're having here that is linked to the digital twinnings is that we need to improve our efficiency and productivity, which in turn means for us to absolutely reduce the CO2 emissions. And in order to do that, we have to digitalize as many processes as possible. And I think digital twinning is definitely a valuable approach to that. And then the last thing, it is about the need we are having of connecting intelligence and not only people and things. And that is the reason why we are thinking of 6G now. Yeah, if we look at the 6G, we have already many initiatives ongoing globally. This is just a snapshot. I have improved one of the slides I got from the European Commission. What is remarkable are, we could go through all those details, but what comes to my eyes are at least 2 things. So first, we have now in Europe more investments than what we had when we were working on 5G within the 5G PPP initiative. At the time, we had 700 million, and now they are discussing about 900 and more millions over an horizon of 7 years, where earlier we were over an horizon of 10 years. Also, remarkable actions ongoing in Japan, that the government has recently committed 2 billion to support the industry research on 6G technology. So within the time frame 2030, although I think that the research will terminate much earlier than that. So I think a lot of this budget will be devoted to innovation and test cases and verification in the field, like we had within the Horizon 2020 in Europe. They have put in place special interest group, like Beyond the 5G Promotion Consortium, where the university and other organizations are working together, and they have played to deliver commercial services by 2030. But more interesting is, I think, the statement that the government made that they are attempting to reach our 30% of the global market share for the base station and other infrastructure by 2030. So there is a lot ongoing, and it is a very, very, very hot topic. And I think that the system will be coming, relatively speaking, compared to the 4G and 5G even earlier. Now, what are the new use cases, what we are thinking of, and what are the corresponding technology requirements? Basically, in terms of technology requirements, like in the earlier generations, we think of improving them on average of a factor of 10, let's put it this way. Use cases, I think most of those use cases are the ones we envision, we put together back in 2015, 2013 for 5G, but you see the technologies basically are still not able of making all those requirements, technical requirements that will allow the communications and delivery of specific service applications such as tactile and haptic communication, for example. In order to have those in place, you need to have a latency end-to-end between the 2 points below 5 milliseconds. If you think an holographic rendering, for example, you need to go even below those numbers, and practically the system has a very hard time to achieve this goal. But more importantly, I think, is the way we need to have in place to connect the intelligence. So being AI, the most important enabling technology, driving the research and later the development of next generations of mobile communication system. If you look at the corresponding requirements, we didn't have strict requirements of energy per bit for the 5G, as we didn't place requirements on jitter, which is now expected to be there. Speeds, yes, as I said, we're expecting at least 10 times more. We are thinking of even up to a terabit per second. The spectrum, that is a key important element that will go up to, expected at the moment, up to 10 terahertz. So by going so high in frequency, we do have plenty of other possibility and application. I'm thinking of sensing, and I will show you later what I mean by that. Okay, in addition to this, we have a very wide coverage that especially allowed by the satellites. Satellites, the one being no longer optional. So the non-terrestrial network are an integral part of the system itself. Yeah, reliability has to be enhanced if you want to meet those the requirements related to those, in relation to those particular use cases, and then the capability and ability of integrating many more connections than using the new radio. The precise positioning and tracking requirements is also improved over a factor of 10, and it's not only, say, 2D, but the expectation are also 3D, because the 6G is expected to provide connectivity not only on ground, but also, yeah, on air, on the space in general at different altitudes. Yeah, there are also expectation and requirements in terms of security. I just placed here the link where you may find more information. It's a very interesting paper published by ABI Research, and I think you may look into that offline. So I would like to present a view of a network vision of 2030 and beyond. So the target of 6G is to realize and bridge the physical world and the cyber world. And in order to achieve this goal, we are currently thinking of new communication channels. And those channels are, say, in a high level, 3 in the downlink and 2 of them in the uplink. So we have the virtual channel, tactile, and inference channel in the downlink, as there is a need for the physical world to communicate with the cyber world through virtual reality. So virtual reality will be the technology that would allow the communication between the 2 worlds. The tactile signal and the haptic feedback will be an integral part of the communication channel, and the inference, the memory, the parameters, the possibility of exchanging the model, the train model between the 2 PI entities, it will be an integral part of the system, which is not today if you consider the 5G. I will show you now an architecture where 5G now in a second. Uplink, of course, we are thinking of sensing capability, learning capability. And one of the challenge will be exactly how to compress, transmit, transport, and elaborate with confidentiality integrity such a large amount of information. Then there are technology coming in terms of transmission. Here, one enabling technology is the quantum key distribution. And what is also shown on this slide, to me, key, in a sense that AI is really one of the fundamental enabling technology that will lead and transform the way we are communicating. And the AI is also thought to be sold as a service. I would say that we will be able to go beyond that, because more than artificial intelligence, which is already today offered as a service. So like Google does, many other providers do it. Yeah, you may have that as a service and pay as you go by download your skills as you need. What I think what will be made available is knowledge as a service, reasoning capability as a service. By the way, this is a kind of architecture was already conceived. As I see, the really new use case is the connected intelligence in a way that was not truly integrated and well represented within the vision we had at the time of the 5G. But for example, Manzardini and I had already a view that this is practically required to have in place. And if you look at what we published back in 2015, it is very much aligned with what you're having today within the research community. At the time, we already envision all the fundamental enabling technology, especially the sensing. You may see here the possibility of having a neural center in the place of data center, neural edge at base station with edge computing capability, and the possibility of interacting between objects where the intelligence is completely taken out from the robotic platform, placed at the edge, so that what I said at the time, and that's going to happen at some point, that the platform, robotic platform, they don't need to spend much time into the learning capability. That's why I don't believe that the machine learning is sufficient, cannot be sufficient. Because what we need to have in place practically, it is a communication system that makes it possible to any physical element to meet among themselves into the cyberspace, not in the physical space. I mean, if you consider humans, it takes us 20 to 25 years to become truly independent. That cannot, it's not required for machines. We don't need to spend much time, that's my point, on machines. We need to have a system that allow an easy path, an easy access to virtual resources, and with the capability and ability of detecting the geometry, and then through an exchange of identity. That's why security is so important. By authenticating your object and exchanging, identify your object, and when you're authorized, you can get all the resources and knowledge as it is represented centrally, so that you can make centrally and enforce at the edge any kind of decision. This is, to me, the real aim. We need to achieve this goal. We couldn't with 5G, and that's gonna happen, must happen into the 6G. And 6G needs to connect intelligence, which I define. Intelligence means any function or functions with ability to represent knowledge and then process this knowledge and then makes decisions. And all of this has to happen at the edge, not on the platforms. And that could be solved by simply exchange and authorization protocols between entity in the physical world, and all the rest must happen into the cyber world. That's what I believe. And that is what will allow us to have plenty of business model. But the difference of today, we have business model, but there is no business case behind. So the only application we're having still on 5G, it is speed test, nothing else. So we need to go beyond that, and we need to have a different way of realizing our infrastructure, communication infrastructure, in particular, having ability of creating new services and make all offering all as a service, including artificial intelligence and knowledge. So what are the enabling technology? And then I'm concluding this speech because I already said beyond the shadow, I'm sorry. So we have identified 5 key enabling technologies. So the first thing, the first paradigm shift, it is about, is a must. We need to shift from NNI, enhanced system, that is 5G. This is basically a detailed machine learning pipeline specified by the ITU, and now coming step by step, bit by bit into the 3GPP. You see here, we are enhancing those capability of communicating by integrating the machine learning pipeline. We don't want this. We want something that shifts from being enhanced, so AI only improves, say, the operations in the system, the performance, even cybersecurity, anything. We want to have a system which is AI native, and also use AI across the communication channels. So the communication channel not limited to the inner channel capacity, but also communicate through semantic channels, which means through meanings. And that is possible because through meanings means that we can use AI, the PI entities, to extract the meanings of what has been transmitted between the 2 points. There are already platforms available to achieve this goal. The second paradigm shift is about moving from cellular, or in general, I would say, terrestrial type of access network to something that has a ubiquitous access. And here I'm thinking of a native introduction of LEO satellites. This is a fundamental enabling technology. And for example, Rakuten has announced the joint venture together with Vodafone Global with the AST Space Mobile, and that is exactly to achieve this goal. And what is it? So I mean, if you think of the deployment of LEO satellites, what we have in practice is that the LEO satellites, LEO constellation, can achieve latency below as you deployed fiber. And this is because the orthodromic surface distance, it is larger than what you will need to cover to connect the 2 points through the satellite system. So here you have an example. For example, if you want to go from, I don't know, you want to connect New York to Shanghai, you see here that what distance you would cover if you deployed fiber, and similarly what you will need to have in place if you connect 2 points using satellites. So that would allow us to really achieve low latency communications and coverage, ubiquitous coverage across all regions. I'm thinking of Australia, for example. In Japan, this communication system is already put in place using AST space mobile. And I hope now we will also have the possibility of enjoying those services in Australia as well, starting from public safety network. So having in place the satellites to allow us to provide the safety services to all the emergency security safety agency. Yeah. So the other three important shifting paradigms is that we need to shift from information-centric network, which is to a sensing system. And this is easy and possible because I was in the Navy. I was an officer in the Navy, and we were using, and they're still using radars. And the radar allows you to have a clutter, to have a view, to understand what is ongoing. Now, if you have in place and the capability of operating at very high frequency, the wavelength reduces. The wavelength relates to the resolution you may have in the clutter, so in the echo of the information you're having when you radiate at the base station through pulses, for example. That would allow us to have a complete view, to sense the environment, and this capability could be integrated into the many functionalities, not only handling the radio resources, but there will be many more services. On top of that, as also sensing could be offered as a service. Security has to be enhanced. So I spent a lot of time today on security. So I think I gave an idea how that was designed for the mobile communication systems, 4G, and then enhanced in 5G, further enhanced into the towards 5G advanced. And I think it will be now time for us to look beyond that. For example, if you look at the privacy now, you do have a consigning algorithm, which is making use of, just in PKI, so that you do have a public key stored, and there will be just provision your SIM card, and then your IMSI, so your international mobile, your subscriber identity is concealed, hidden since the very beginning in the communication. I think we need to go beyond this approach, and we could use AI as it is used today. AI into the, I've seen many kind of application in healthcare where you have a PI data, so personal identifiable information, which is concealed using machine learning. I think that is definitely an approach much more robust and violent when we think of. Integrity is all over the place, is using hash functions and true message digest. And I think we have now an opportunity to explore distributed ledger technologies, and we are all familiar with blockchain. There's still many challenges to achieve integrity with DLT, but yeah, you may think of the workloads and how the blockchain in specific implementation works. That's definitely impossible because it has to be instantaneous. So we can only wait the authorization of ledgers to be in place, or whatever how we intend to use this technology for such a long time. So that's anyway an opportunity for us to use cryptography. It's all based on a shared secret. And yeah, I think we could go beyond that and work on post-quantum cryptography. And yeah, and what we want to do is to create quantum resistant ciphers that even the future quantum computers cannot crack. So that's the idea beyond that. And then security, I think it is expected now by design. And security by design, I think, has to implement necessarily a zero trust model. So we need to have in place and implement a defense in-depth strategy augmented by a zero trust model. So that also would require one-day discussions. There are many approaches to that. One is based on resources proposed by the NIST, which is one of the most interesting framework in place, but practically means that you trust nothing. So you assume that the list level of privileges, and you are simply authenticating and then authorizes any kind of exchange between any sort of peer entities, whether the entity is a whatever, it is a container, it is a piece of hardware communicating with a piece of software or anything. I think that's one way to move forward. And finally, I think it will be now the time to shift from an operator-centric system, which is nothing else than a generic bit pipe. As I said, still today, the most used application is speed test, to something that is truly prosumer-centric and by nature support a number of business model. And if I look at, for example, at the Rakuten approach, it's definitely through virtualization to enable a number, plethora of new business model. That's the way forward, and think also beyond that, when we will have a possibility of finally achieving a full immersive interactive experience with the ability of further reducing the latency and make the system even more reliable as it is a 5G today and in its upcoming future releases. This is my last slide. What I think we are aiming at here finally is an architecture or a reference architecture as illustrated on this slide. I'm not going to the details of the implementations, as I'm expecting it's going to be all virtualized, run on efficient point of presence. But here you do have a view of the different functionalities, interfaces, and architecture that will integrate any type of access in a converged manner, where also we have the possibility of offering services on ground, on air, and also on space. And here you have the different altitudes. It's not on scale. It's not on scale, so but basically gives you an idea of the system, how would that look like. So already in release 17 5G, we will support geo communication as I presented earlier. LEO will be key as an access technology, not only as we are using today as a backhauling technology, but we are expecting access technology. We have ability to integrate among area vehicles as well as the AJP and aircraft, and on Earth, on the ground, we will have the opportunity of integrating any kind of access, as the Wi-Fi will also evolve as it will be the 5G towards 5G advanced. And then we will have a potentially fresh new radio access technology, which will be named actually, yeah, we are already calling it 6G. So I think that's pretty much what I wanted to introduce you today. And I mean, all details you may find are in the paper. And the paper also has 30+ references where you can go deeper and think of developing further your skills, or graduate, or even say become an expert into that specific domain and contribute to the realization of the vision I have attempted to present in about an hour. So thank you so much for having me today.
Thank you so much, David. So the session is gonna to be automatically ended at 6:30. So we still have some time, 6 minutes maybe, to answer the questions. I've seen 2 questions in the chat from Leith. So let me see.
Let me see if I start the video, whether you can see me.
Yes. So Leith, would you please ask your question, or do you want me to just read the questions?
I'm happy to talk about it. David, for this audience, you want to talk a little about the relationship with IEEE 802, and in particular, do you think there's a possibility that the IEEE 802 standards will finally roll over a lot of the detailed standards that you've been talking about for communications?
I'm sorry, you mean the evolution of the so-called Wi-Fi, LoRa, and other type of access technology?
Yes, well, all of those, and Ethernet comes in there and other things like that as well.
Yeah, I mean, there is market for all those technologies, because if you look at the Strata now, I think the IoT has a lot on LoRa. Of course, I am a guy who comes from the cellular, so I strongly believe that the system will ultimately converge into cellular, and then it will be on satellites integrated with cellular system. But Wi-Fi, so the standard, the IEEE standard will continue, will still be there. I have made a table of, it's not on this presentation, but yeah, I'm happy to share that. That will evolve, it's gonna coexist. So there are specific use cases where you do have a Wi-Fi access point, and Wi-Fi will evolve. We need to be careful because Wi-Fi 6, for example, we are expecting maximum 50 meters coverage. And yeah, there are vendors that have enhanced also the radio resource utilization. So you have a sort of a handoffs, sort of mobility between access points, but it's still not designed, because if you introduce all those capability and functionality, it becomes too expensive, so that will vanish. No one would deploy Wi-Fi. At that point, it's more valuable to deploy the cellular system. So said this, I think, yes, they will evolve and will be integrated and an integral part of the system as they are today. And today already, with the introduction, the 5G core network, you may use seamlessly, and your smartphone where you are using next generation SIM card that allows you an authentication, authorization, and accountability through Wi-Fi, as well as you're having with your, say, cellular access provider. So the answer is yes, they will coexist. That's my view, of course, they will coexist. There is opportunity. I don't think is a matter of the access. So I think the main development here will be on a converged system that will allow us to enjoy services pretty much using any kind of access. So the challenge will be for us to have a virtual approach to the implementation that will allow you an easy upgrade so that any kind of access can be integrated into your service portfolio to delivering. So it's just a sort of, is a tap to the ocean that you're having in control through virtualization to me. And Wi-Fi will be there. I marked here, especially see a Wi-Fi 7.
Okay, all right, thanks. My other question is at the other end of the scale of the things you're talking about is, you talk about putting all the intelligence in the edge, and that probably then for functionality requires guaranteed low latency, but you can't guarantee that in a public network. There's always times when public networks get overloaded one way or another. So how would a system that you envisage cope with that?
Yeah, so the point is that until we are able to meet certain performance requirements, I'm thinking of latency. There's no way we can enable new service applications. So it is a time for us also on public network, if we want to think of having in place new services, and also for I'm thinking of the carriers have new way of monetizing. There is a need here to open up the edge. So if you want to reduce latency, the way to do that is to go closer, because it's a simple math. So the speed of the light to have to go below a millisecond two-way latency, you cannot go more than 150 kilometers. So said this, I think at the edge, it is a topic that and the multi-access computing platform, I think it will be integrated and offered as a service, even on public networks, independent of the access, because as I said, it is convergent. As we speak, for example, here in Australia now, there is an initiative called ITRP. Within this initiative, exactly one way is to think of having a capability in place, even on top of a public network, to reduce latency, and definitely the multi-access edge computing platform. It is a viable approach to that. Yeah. So I think we need to change something like if you want to have new service applications, and latency has to be achieved in a way or another. We can keep using speed tests. Yeah.
It's okay. Thanks.
Thank you so much. Any quick questions? Thank you so much, David. It was very interesting talk, and thank you so much for accepting the invitation. And hope to see you all guys in the next talk. Thank you.
Thank you so much for having me.
Thank you so much. Bye. Have a good day. Bye.
Bye-bye.